So if you have the option to turn on the video, it would be great, so I can feel like someone, there is a live person on the other side of the screen. Thanks, Ronnie, Oz, Homer, Roy, Anika, Maor, Gadia, Lirom. Okay, nice to meet you, everyone. Okay, so this is the first session of a 4 hours or a 4-meeting mini course on quantum computing, and the goal is to bring you to a situation in which you are able to run your own quantum simulations, quantum computation on a real quantum computer by IBM. As I will tell you towards the end, actually IBM is now offering a very generous free credits for academics, which will really allow you to to do whatever you want, or almost whatever you want. And this is so this course is organized together with the group of Eliar Bell from IBM. And actually the last meeting is going to be an in-person meeting in their headquarters, for those of you who are interested, of course. And also with QERNEL. So as you know, QERNEL is a research hub that was established by the Council for Higher Education in Israel and includes 22 researchers from all the main universities in Israel, dealing with real life, I would say state-of-the-art quantum computing applications of different types. So the lecture today is like an introductory lecture, I would say like a motivation lecture. Why is it interesting and what can we expect to gain from a quantum computer? It's going to be about an hour and a half. We'll see how it goes. And of course, feel free to ask questions by just unmuting yourself or writing in the chat or whatever. So what else? Yeah, that's it. So, okay, so our first meeting today is about quantum simulations of many-body systems with quantum computers, a global overview. Of course, the field is huge, so I've selected only a few examples of what can be done with modern quantum computers. So essentially, my lecture today is going to be divided in 2 parts. In the part number 1, I'm going to show you the state-of-the-art of quantum computing, and I'll try to give you an intuition of what can be achieved on a quantum computer, what are the parameters to look at when basically planning an experiment with quantum computers. And in the second part, I've selected 3 examples of quantum simulations from 2025, 2026 by different companies. So I'll showcase different examples of different models, also different companies, different platforms. So you'll have, sort of a feeling of what's going on in the field. Of course, it's, as I mentioned, there are now really, it's a blooming field. And I really hope, that's my hope for this meeting, and this is why we are organizing this meeting, that at the end, some of the participants, maybe all the participants, will feel the need to run their own quantum simulation on a quantum computer, and we'll have many more research studies done on quantum computers that, coming from these meetings. And, many of you, so some of you I already know, you've already done some experiments, but some of you are new, and that's the idea. Okay, so let's really start. So in particular, what I have in mind is quantum computing on the cloud. So the idea is that we are not experimentalists. We cannot build our own quantum computers. Of course, there are some research groups that are trying to do that in the academia. But the truth is that to build a quantum computer, you need a huge amount of funding that goes much beyond a single research group. So for a research group, even in a big university, it's very hard to make their own quantum computer. So instead, what we will do, what I'm suggesting to do, and that I think why QERNEL was established as a theory research hub, we'll use quantum computers that someone else has built. So the race for quantum computing on the cloud really started 10 years ago, and IBM was the first to offer such a service, and I think they were really brave. I mean, at that time, they had a 5-qubit quantum computer with 95% fidelity, which means that every time you apply a gate, you make a 5% error So essentially, after you apply 20 gates, there is no signal left, right? So it's really a very, very tiny and noisy quantum computer. But I think they were really very brave, and they put it online and say, okay, look, this is the future. Try it, and let's build a better quantum computer together. And their dream, in 10 years from now, I think they were right. So nowadays we have many more companies offering such a service. So quantum computers to which you can just connect, pay per hour, or get some free credits, or collaborate in a way or another, and you don't need to build your own quantum computer. You can use those quantum computers. So of course, there are quantum computers in many different countries, so in the Americas, in Europe, in Asia. Here I added also the Israeli Quantum Computing Center, which is, as you know, a joint venture of Quantum Machines and the Innovation Authority of the Ministry of Economy. And it's located next to Tel Aviv, and they have also a small prototype of a quantum computer. So I won't discuss that today, but this is also an option. So those quantum computers, of course, they differentiate geographically. So you have in different countries. Maybe that's not very important. After all, we are connecting through the cloud. So where it is located, it's maybe not so important. What is important is to differentiate the different quantum computers according to the technology that they are using. So currently, the three main platforms that are leading this race are superconducting quantum computers, most prominently IBM, Google, Rigetti, and D-Wave, and others. Basically, the superconducting quantum computer is created by lithography. So these are basically wires, superconducting wires, and there are small loops. So here, okay, I guess the audience is very diverse. So there is a whole theory of how you build a superconducting quantum computer. Just let me give you one intuition for those of you who are new, which essentially the idea it's a very simplistic, it's not exact, but just to have something in mind, think of a loop in which you either run current or not, so that could be your 0, 1. It's much more complicated, but think of it, just to have something in mind. But anyway, these are created by lithography, and they work at very small temperatures. You need to put them in the dilution fridge. And that's actually important because you don't forget that we live at room temperature. So you need to bring your signals from room temperature to the ultra cold temperatures of a dilution fridge, and that's a serious limitation for quantum computers based on this technology. The other two technologies are actually, I would say, hot technologies in the sense that they work at room temperature, and they are trapped ions and cold atoms. So in trapped ions, you trap ions, and use just, as you know, they respond to electric fields. So use an electric field, actually a time periodic electric field, to trap them. And in cold atoms, instead, you use basically microwaves or lasers to control them, usually. And these are just neutral atoms, and then you use different levels of the atom to excite them. There are also quantum computers based on photons, but for the moment, they are not gate-based quantum computers. So they are like quantum computers of different type. People speak about building quantum computers with photons. There is a lot of investments, but not something that you can use right now. So I think if you're interested right now in running an algorithm, and I will give you examples of something that has been done on superconducting, trapped ions, and cold atoms, and maybe I will mention a little bit this difference. But I think this map is key to us. And of course, yes, these numbers, these are very important. I'll come back to these numbers later, but in the most modern IBM quantum computer, you have hundreds of more than 100 qubits, and the fidelity, if you remember before, it was 95%, so there was a 5% error every 2 qubit gate, and here you have a 99.8, so you have 0.2% fidelity. And I'll mention, as time goes on, what these numbers mean. They're very important for us. Okay, so essentially this is the point we stand. So we have access to a quantum computer with, say, 100 qubits. What's next? I mean, what should we do? And this is really what I'm interested in exploring today, and what I encourage you to think about. Just while I'm talking, run your neural networks, your neurons, and think of what could I do with a 100 qubit quantum computer. I'll just give you some examples of things that I missed on. So I think that when speaking about quantum algorithms, I would split all the quantum algorithms in two categories. This is very rough, but I think it gives you a way to think about it. So you either use a quantum computer to solve a classical problem, or you use a quantum computer to solve a quantum problem. So when I say classical problem, there are actually, I would say, three main examples of quantum algorithms. This is also something peculiar to quantum computers, that there are not many algorithms. It's actually very hard to develop a new out-of-the-box quantum algorithm that has some purpose, that helps you in some practical, just thinking of a game, fine, but something that is really helpful. There have not been many examples, and the leading examples, as you probably all know, it's the Grover search algorithm, Shor's algorithm for factoring integers, and let's say the HHL. I'm mentioning this also because Hasidim is a professor at Bar-Ilan University. Actually, he did this was a part of his PhD thesis, and I don't know, I tried to get him involved more in quantum computers, but I see some resilience. Anyway, this was a huge, one of the main contributions. And you all know, the search algorithm. This is related to the field of optimization. So people say, okay, you need to solve a search problem, like a complicated logistics problem, finance problem. And here it says, see, Quantimize. So Quantimize is a young startup at the time, the chief scientist of, which deals with using quantum computers of this type of optimization. So if you find this specific, direction interesting, please talk to me. Of course, you all know that quantum computers can break the RSA. There were recent news from Google that they can do it maybe in 3 years from now, etc. So you've always all heard the news, and okay, this is great. This is not the topic I want to talk today. What I would like to focus today is on the other side of the table, which is how to use a quantum computer to solve a quantum problem. And what do I mean by quantum problem? It's usually, I would say, one out of 3 categories. Again, this is schematic, but I think it gives you the idea. So it's either something coming from chemistry, so a molecule, usually, a big molecule, you're trying to simulate the ground state or the dynamics. It could be something that comes from quantum physics. So usually when we speak about physics, we speak about many-body systems, systems with many degrees of freedom. And usually what you would like to study in a quantum computer is the dynamics of those systems. Maybe I'll mention a little bit the difference between ground state and dynamics in the examples that I give you at the end, later. Or that could be just a theory problem. So I would say quantum information problem, something that does not come from nature, it just comes from an interesting thought problem. And in particular, you could think of simulating a random quantum circuit. So clearly, a random quantum circuit is not something useful, right? Usually you're trying to solve a molecule or a material. You don't want to solve a random circuit. I would say, in terms of physics or chemistry, random circuit is just the worst thing you could do. You just don't know, you don't even know which circuit you're running, right? It sounds like a very crazy idea, but it's actually interesting. So it's interesting from a basic science, and the kernel is about basic science. So I really encourage you not to focus too much on how this can be useful to bigger and better fertilizers, because that will take forever. Think more about what could we do that is relevant, interesting, related to topics of basic science, and demonstrable on a quantum computer. That's the focus that we are taking at kernel. Well, there is also a third direction, which is, so I said, you could either solve a classical problem, solve a quantum problem, or don't solve any problem. And that's when people speak about quantum and AI. And I have not been it's not very clear to me what they really mean by quantum and AI, apart from the fact that quantum is a buzzword, AI is a buzzword. So it's not very clear to me what you could do. But, if you have some crazy and nice idea about quantum and AI, that could be really, really great. Okay, great. So, great. So let's focus here. Okay, yeah, I'll mention actually machine learning a little bit later. So, there are things that make sense, but I'm saying that there seems to be like a buzz about joining quantum and AI, but I have not seen it very clearly coming, in practice. Okay, so we want to focus here on solving a quantum problem, as I mentioned, and let me give you the first example from quantum information. This was actually a simulation of a random quantum circuit, and in particular, I would like to talk about Google's quantum supremacy. I find this an amazing experiment. I mean, I still, 7 years later, I think this is one of the, I mean, maybe the first really beautiful experiment that was done on a quantum computer. So I really, and if you haven't read carefully this article, I think it's worth doing that. So for those of you who don't remember or haven't seen it, what is this quantum supremacy, Google's quantum supremacy experiment about? So essentially, what they claimed is that they were able to solve in 200 seconds a problem that would take on a classical computer 10,000 years. And the reason of this gap between 200 seconds and 10,000 years is the fact that they are using quantum computer with 53 qubits, and so the Hilbert space has size 2 to the 53, which is 10 to the 16. It's very large. So when we actually had last year, we had the opening kickoff meeting of the kernel, I said something which was then corrected by people in the audience. So I really like to get some feedback. Sometimes I make mistakes like everyone. I said, okay, this is a beautiful experiment. No one was able to really break it, and that was not right. In fact, already in 2025, a group published from different universities in China, they published a paper. It's called Leapfrogging Sycamore, harnessing 1400 GPUs for 7x faster quantum random sequences. So essentially, they were able to reproduce the results of Google faster. Okay, so if Google took 200 seconds, they did it seven times faster. What I would like to highlight is nevertheless that they actually used 1400 GPUs. So apart from the question, where did they find those 1400 GPUs, but which I'm not going to touch upon, if you make a small computation, you will see that 1400 GPUs is actually equivalent to 10 to the 14 transistors, right? So in each GPU, there is a huge amount of transistors, I think a billion. And so if you take 1,000 GPUs, you really have a huge number of transistors. And in a sense, what this work is telling us is that these 52, 53 qubits actually are equivalent to 10 to the 14 transistors. So maybe the time was shorter, but you needed a huge computational power. So yes, people were able to sort of break the Google supremacy, but at a very high cost. And I think this is why I'm still so, I think this experiment is so beautiful. I mean, it's really showing us something very peculiar about such a small quantum system. It's really hard to simulate. Okay, great. So what is the main idea behind quantum supremacy? So what you do, you have a random circuit. So this is schematically the circuit. You're probably, I guess you all are sort of familiar with quantum circuits. So the x-axis is the time, the y-axis is the qubits. So here you have 5 qubits. Of course, in the real system, you have 52 qubits. And what you're doing, you have single qubit gates and 2 qubit gates. So 2 qubit gates are here, you see these arrows that connect 2 different qubits. And the single qubit gates are just blocks. And the blocks were chosen randomly. So that was the idea. So the 2 qubit gates were always of the same time, but the randomness came because of these random, you see these colors. So you see there are different types of single qubit gates, different colors, and they just took a random configuration that they can, you can of course average over many of them. If you want to have significant, statistical significant results, you can do that average. The average is done by just changing the single qubit gates. And so this is a circuit, you run it, you measure it in the end. Good. So what is the goal? So the goal is to show that this state that you have at the end, that you have measured, is actually have a good overlap with the theoretical prediction. So you can sort of theoretically compute what is the state that is found at the end of the circuit, and you want to compare it with the experimental finding. So in principle, naively, you would say, okay, good. So let's say you could compute the theoretical state. Maybe take you some time, but fine, you can take a big computer, you compute it, and then you compute the state in the experiment, you see which state you have, you compute the overlap, and that's it. The problem is that because the psi experiment is a state with 53 qubits, so it's actually superposition of 2 to the 53 different states. And so if you want to know which superposition it is, you would need to perform 2 to the 53, or because these are classic, these are complex numbers even more. So something like 3 to the power 52, 53. I mean, if you want to know which state you have at the end of your experiment, okay, 5 qubits is fine. But if you have 53 qubits, that's terrible. So the idea is that there was a challenge, a theoretical challenge, which was assuming that I can run the compute, the circuit, how do I know which state that you have at the end? And the idea really came from the idea of cross entropy. And again, I apologize, I'm not giving here the references. I'll add the references in the PowerPoint later, but you know, this is very easy to find. So the idea was the following. What you do is you do your experiment and then you measure. And let's say you measure it 100 times or 1,000,000 times. In this case, it was about 1,000,000 times. So you measure the end state 1,000,000 times, and then you compute something, which is 2 to the power n, and is the number of qubits, times the sum of the probabilities of finding the bit strings that you find in the experiment theoretically. So let's say I have 1,000,000 experimental results. For each experimental result, I compute what is the probability in the theoretical state, you know, in psi theory. This is just the overlap of psi theory with the bit string square, and then I sum all of them. Okay, that's essentially the cross entropy. And of course, you divide by the number of outcomes. So if you do this calculation, you will find that if the theoretical state equals to the experimental state, so if the probability of finding a state in the theory equals to the probability of finding a state experimentally, in this case, you will find that this sum gives you a number 2, gives you 2. If instead the p-theoretic, the experimental is just a random, you know, you have just extracted random bit strings, it's just complete noise, then this sum will give you 1. Okay, so intuitively the idea is that the 2 means that you have found more probably states with a larger p-theory. That's the idea. So if you have the right state, then you'll more probably find the correct theoretical state. So that's why p-theory of the experimental results is higher, because you more probably found state with larger p-theory. That is telling you that the theoretical state was similar to the experimental state. Does this explanation make sense? Yes? Okay, thanks, Omer. Someone is not. Okay, thanks a lot. So then they said, okay, fine. So if this is the case, yes?
Does this computation is more efficient than just calculating the f, or it is just a way to show how to calculate f?
So the idea, so you use this to compute f. If you want to compute f from above, you would need to perform 3 to the 53 experiments. So it's just impossible. You will need to wait forever, right? 5 to the 53 is 10 to the power, it's 10 to the power 5. So it's like a huge, it's 10 to the power 15. It's a huge number. So you would need to wait forever. You cannot do it. While for this cross entropy, you can choose how many experiments you do. I mean, it's enough to do, let's say, 1,000 experiments, 1,000,000 experiments, and so it's much easier to realize. That's the difference. And then you can say, if once you have computed the XEB, you say, okay, XEB minus 1 is the fidelity. Why? Because if the fidelity was 1, meaning that I got the correct state, then XEB would be 2. And if the state was random, meaning the fidelity was close to 0, it would be 1. So the fidelity, this is an approximation to the fidelity. It's taking the cross entropy and subtracting 1. That's the way you extract the fidelity. Okay, so I'm bringing this up because it is very important when planning your quantum experiment to think of what are you going to measure. Because if you take many qubits, then measuring the final state is going to be a problem. So you need to find a smart way to probe the correlations or the observables that are of your interest. Because you cannot compute the state itself. Computing the state itself is fine if you have a very small system, but once you grow beyond 10, 20 qubits, it's going to be impossible to know the state itself. Okay, so in this experiment, this Google supremacy experiment, there is also an important graph, which is this one. So this is the result. So this is the fidelity as a function of the number of qubits in the circuit. And you see that the number of qubits goes between 10 to 52, 53, and the fidelity goes down. So the more qubits you have, the more errors you have, and that's why the fidelity is going down. And what you see in this plot is the comparison between the experimental result, so the circles, x's, and plus are experimental results, and the black line. And the black line is obtained in a very simple way. It's just obtained by multiplying sort of the survival probability. So let's say let's assume that you have 2% error per gate. Okay, so you take, and you know that, let's say, for 35 qubits, you can compute how many gates there were in your circuit. So it depends, of course, on the number of circuits and on the number of cycles. And then you basically just multiply, right? You multiply this 99% to the power number of gates. So essentially, there is, as you can see from this plot, there is like a dashed line curve, which is a very good approximation of the fidelity. I think it's very useful to understand, what to expect. So of course, the graph is more complicated. I mean, it's not a one-to-one, but you see that it's sort of following the trend. And I think understanding this trend is very important. And the trend is telling you that for this particular experiment, the fidelity would go down as 0.98 to the power number of gates. So if you want to know what is the fidelity that you expect to have, just take the number of gates that you have applied it and take the error. So in this case, it would be a 2% error. Don't forget that this experiment was performed in 2019. So it was already many years ago. In that time, the fidelity of the typical fidelity was about 98%. It was already better than the first IBM, right? It went from 95 to 98. Now we are much closer to 200. But at that time, this was already a very huge success. Okay, so let me bring this one step further with something I call the practitioner's thumb rule for quantum volume. So what is quantum volume? Quantum volume is asking the following question. It's a metric that was invented by IBM, and essentially is considering a square circuit. So it's asking how, take a square circuit where you have n qubits and n layers of 2-qubit gates. Okay, so the x, both the y and the x, they are both of the same. In this case, it would be n equals to 4. And then if you want n equals to 5, you would have 5 qubits and 5 layers, and so on and so forth. So and then you ask, what is the largest circuit that I can run which has a meaningful fidelity? Something, I don't know, 50% fidelity. There is a specific number. It doesn't really matter. So you're asking, what is the largest circuit that I can stand run sort of with a reasonable fidelity? Then they did like a trick, so they said, take that number and take 2 to the power 4. Because they want to have like exponential increase, so they said, so in this circuit, the quantum volume wouldn't be 4, I would think it's 4, but actually they said it's 2 to the 4. Okay, so you take the largest square circuit and then take log 2 to the power. That's called a quantum volume. Now, if you follow this sort of very simple thumb rule, where you say what is the fidelity? The fidelity would be 1 minus epsilon. So epsilon is the error per 2-qubit gate, to the power number of gates. And in this case, how many gates you have? You have essentially n squared, right? Because it's a square circuit. So you have n squared over 2, because you have pairs. So you say, well, then I can estimate the fidelity as being 1 to the minus epsilon. Again, epsilon is the error per 2-qubit gate. By the way, I didn't mention it, but we always look at 2-qubit gates error. Why? Because single qubit gates errors are much smaller, so they are not dominant. What is really the problem is when you try to apply a gate between 2 qubits. So you take 1 to the epsilon to the n square over 2. Then I said, well, maybe you can just approximate. If epsilon is small, you can approximate it to 1 minus, okay, like a Taylor expansion. And so this is, okay, fine. And then I give a thumb rule and I say, what is a circuit which is good? I mean, what is a reasonable assumption is when the fidelity should be at least 1/2. So when the fidelity goes below 50%, that's where troubles kick in. I will mention maybe later what we do in that case. But this could be a reason. I mean, if you're planning your experiment, usually try to hit the 50% fidelity. Don't go lower than that. You will see a very weak signal. Of course, there are details, there are also tricks, I'll mention them later. What does that mean? That means that if you take these two equations together, you have now an estimate. And the estimate tells you that the the logarithmic of quantum volume, I mean this n, which is the logarithmic quantum volume, goes the square root of 0.5 divided by epsilon, where I mentioned, again, epsilon is the 2-qubit error. And if you look in the recent literature, you will see that this estimate works very well. So this is, of course, these were very complicated experiments in which they really realized those gay circuits and checked the fidelities, etc. So they work hard to make this table, but the table works very well with the formula. I think even my formula is a little bit better than the formula which was given by IBM. But okay, they are in the same spirit. To summarize, and this is the key important, maybe the one thing I would like you to remember from this talk is this equation. The number of gates that you can apply in your circuit and still make meaningful result can be approximated as 1 over 2 epsilon. Okay, that's the idea. So if every gate gives you an error of epsilon, don't go lower than 50%. That's my thumb rule for you. So if you want to think of how big can be my circuit, you need to know which platform you're using. You can, it's very easy to find this information. What is the typical 2-qubit error, which is epsilon? You take 1 over 2 epsilon. That will tell you how many gates you can apply. And then you can make it square, you can make it whatever, but that's an idea. So for the state-of-the-art superconducting quantum computers, epsilon is of the order of 0.2%. Remember, it was 5% 10 years ago. It's now 0.2%. It's really, they work really hard to improve that number. And that means that the typical number of gates you can apply for a quantum circuit and still make something useful or meaningful, it's about 250 gates. And I can say 250 gates, it's already a significant number. I mean, you can think of doing an experiment, a meaningful experiment with 150 gates. Don't plan on building a circuit with 1 million gates. That won't work. 250, maybe a little bit less, maybe a little more. Depends on the tricks that you'll use. I'll mention a few tricks later. Okay, great. So I'm doing, I think, very well with time. So what I've discussed with you is a way to estimate how many gates you can have in a quantum circuit. And I just have a last slide for the theory part, and we'll go to the applied part. My last slide for the first part is, in general, when you think about quantum algorithms, we discussed that you can classify them according to whether they are solving a classical problem or a quantum problem, or you can classify them according to the methods. And of course, again, this is a very oversimplified picture, but I think it's telling us something. And I use these symbols, so like play, replay, and restart, to tell you that there are, roughly speaking, 3 categories of circuits, of algorithms. Those that require a single quantum circuit, okay? So you give me the circuit, I run it. And for example, Grover is such a case, right? In Grover, you give me your problem, I run the Grover, get the result. Or Shor's factorization, again, you give me, a number, the input number, I run Shor, I get the result. And also many-body dynamics. This is also the case. I mean, this is the topic that we'll discuss further as in the second part. But many-body dynamics means that you know what the Hamiltonian is. Usually, you need to give me the Hamiltonian. You give initial state, you give me the Hamiltonian. I prepare the state, I run the Hamiltonian, I probe something. It's deterministic. Okay, these are deterministic quantum circuits. Well, of course, there is always a matter of of randomness in the quantumness of the problem. So sometimes you need to get, statistics to average over the quantum average. But the circuit itself is deterministic. It's a well-defined circuit. Then there are approaches in which you instead you want to run the quantum circuit many times and actually post-process the results. And I would say that random quantum sampling would be such as an example. So if you are speaking about a random circuit, then you'll need to average over those random circuits. I mean, you don't want to take one circuit. It's not a deterministic circuit. It's going to be a random, you need to statistically average over those random circuits. If you think about quantum error corrections, they also require some degree of repetition, and also even more so in the case of error mitigation. So error mitigation is, I'll tell you more details as time goes on, but error mitigations are approaches in which instead of running a single circuit, you basically trade more circuits for better precision. So you run many more quantum circuits, it will take you more time, so you need to spend more money, fine, but then you'll get a better quantum result, a better approximation for the quantum circuit. So these are also situations in which you need to run the quantum circuit many times. I mean, the quantum circuit changes, you need to run, for a single task. You have a single task that requires you to run many quantum circuits. But these quantum circuits, I would say they are known ahead of time. So I don't know, well, maybe quantum error correction actually maybe quantum error correction should sit here on the first category, I don't know. But certainly mitigation is a case in which you know ahead of time which quantum circuit you need to run. And then the third class, it's the class of variational quantum circuits. So in this case, you don't know a priori what is the quantum circuit that you need to run, but you discover it while running the quantum circuit. So you start with a trial quantum circuit, you probe it, and then use the result to improve your variational quantum circuit. So it's a little bit like because you don't know how to program a quantum computer, then you sort of guess, right? And then you use the previous results to improve your guess. So this is related to a field called the quantum machine learning. So that's a connection between maybe quantum and AI, but I don't know. And well-known examples is the variational quantum eigensolver. This is an algorithm that was developed that IBM worked a lot on, and it's a method that allows you to find a good eigenstate of a molecule. And the QAOA, so QAOA stands for Quantum Approximate Optimization Algorithm. It's a variational circuit that is sort of substituting the Grover search algorithm. So if Grover search is the run a quantum circuit version of the optimization problem, the QAOA would be the variational version of an optimization problem. So so I think this is important when you plan your quantum circuit. Do you know exactly which quantum circuit you need to run, or maybe you want to run many quantum circuits, or maybe even you want to, as time goes on, sort of have a feedback loop in which every time you learn something and then improve your quantum circuit. So these are three different ways of programming a quantum computer. Okay, so that's the end of part number 1. I think this is a very good time for maybe questions, if you have any.
And I have a question about the Google quantum supremacy experiment.
Yes, please, Zaz, please.
So I couldn't understand if they use like random 2 gates qubit, or they use like one random gate on a single qubit and then C0.
Yeah, so it's not C0, it's a different gate. So the native gates of Google is not a C0. It's basically something that looks more like a XY gate. So something like an I-swap gate. It's not C0. The idea here was that they use always the same I-swap, and the randomness came into the single qubit gates. So the single qubit gates were chosen randomly in a set of random single qubit gates, and the 2 qubit gates were always the same.
Okay. And they did it in order to reduce the error, right? Because how random will it?
Yes, exactly. So that's a very good point. So Google were cheating. And in what sense? That they knew, I mean, the way that they worked, I mean, the result was impressive, especially for that time. And the way they got, I mean, I said cheating, but I meant that they really work, very smart, in a smart way. So what they did, they calibrated the 2 qubit gate very precisely very precisely a specific 2 qubit gate. So if you tell me, oh, I want to take a random 2 qubit gate, then it's going to be very hard to make it precise, because I need to recalibrate every time that you change the 2 qubit gate. If you tell me, no, I want a specific 2 qubit gate, and I'm going to calibrate it precisely, that's the way to get to high precision. So that's the way why in general quantum computers will have a very well-defined native gates. I mean, the 2-qubit gates usually are preset. They are, let's say, control not. They are maybe some ISWAP or some because you need to calibrate. So if there is a I hope this answers the question. Okay, so I see, by the way, Eli Arbel is here. He's in charge of the remaining 2 parts. Yes, more questions? Thanks, Oz.
Hello.
Yes, please, Rajit.
Yes. So, sir, in this slide, the thumb rule. So the like number of gates that we can use. This is only applicable for square circuit, or is it applicable for like if the circuit is in square as well?
Yeah, so, okay, so thanks for the question. Maybe I wasn't very clear. So the definition of quantum volume refers to a square circuit, and that's why you see that this n, which is the size of the square circuit, it's actually like it goes like the square root of 0.5 divided by epsilon. But if you're interested more in general to generic circuit, not specifically to square circuit, what really matters is how many 2-qubit gates you have. So it doesn't matter whether it is square or not. What really matters is how many 2-qubit gates you have, because every 2-qubit gate you add to the story, it will add more noise. So that's why I say this n is the number of qubits in a square circuit, and these n gates is just the total number of gates. So it's not necessarily for a square circuit. It's in general. I mean, you can, okay, in principle you could take fewer qubits and then propagate it for longer, or more qubits and propagate it for less. But these are the numbers that are typical for the number of 2-qubit gates.
Thank you.
Okay, thanks. Okay, great. Okay, so if there are no more questions, let me move to the second part. So in the second part, I would like to describe 3 examples of quantum simulations. I apologize ahead of time that, I had to make a choice. So I chose some. They're not necessarily the most interesting. I chose them because for the diversity. I want them to be as diverse as possible. So not that, if your favorite, don't feel offended if your favorite quantum simulation is not here, which could be definitely the case. So we are going to focus, I would say in particular, quantum physics, just because, okay, this is the field I'm more expert in. And the idea is to perform a quantum simulation. So what is the idea of quantum simulation? Is, let's assume you have a material, it has n sites and atoms and molecules and atoms, let's say, or n, yeah. And if you want to solve this problem, you'll need to, just to describe the state of the system, you'll need to have 2 to the n complex numbers. Right? That's the key point, because the Hilbert space has 2 to the n states, and in general you're in a superposition of these 2 to n states. So you need to have 2 to the n complex numbers. And if you take even just for 30 qubits, you already need at least a gigabyte, well, more than gigabytes, then maybe tens of gigabytes to store the information. So just even to know what is the quantum state, to classically store the quantum state, it's going to require huge memory. So what do you do? Well, you can do it. I mean, maybe you can use a classical supercomputer, which has memories of several gigabytes, and you can get to those numbers. So typically, if you are trying these approaches, this state vector simulation, you can get up to 30. I mean, on a normal computer, it's just usually you get stuck at 20, but if you are very serious about it and you use supercomputer, you get to 30, but definitely not more than that. And the other idea is to use an approximation. So, well, here I wrote an analytical approximation, so some equations, right, to try to solve the problem analytically. That's one approach. Or maybe a numerical approximation. So there are also numerical approximations to compute the dynamics. I'll mention some numerics later on, but eventually you will get stuck at some point, or at least for some cases, the approximation always have some assumption. And so when the assumption breaks, maybe when the system is too large, when too much time goes on, when too much entanglement is involved, any approximation would break down. And really, the first to bring up this idea was Feynman, and said, if I try my best to make the equations look as near as possible to what would be imitable by a classical probability computer, I get into trouble. And so his solution was to do quantum simulation. And the idea was very simple. If you have a quantum system and you want to compute it, don't use a classical computer, use a quantum computer. The field of quantum simulations, I think, this is my impression, I hope this is my own, take, impression. I think it was really pushed ahead a lot by these beautiful experiments of ultra-cold atoms, starting from the celebrated realization of Bose-Einstein condensate, and then the quantum phase transition. I mean, it's an entire field which bloomed in the first decades of our century. It is still blooming. I mean, there are still beautiful experiments, but in parallel to it, there are also quantum computers. So now I think that what you could do once only using simulators of ultra-cold atoms, you can now do also using quantum computers. I think it is very, it's interesting just to explore this opportunity. So as I promised, I'll bring you 3 examples. So the example number 1, again from 2025. So this is a collaboration from Harvard, MIT. I mean, you see the names, and they realized the quantum simulation using neutral atom quantum computer. So a neutral atom quantum computer is basically also known as Rydberg atoms quantum computer. So the idea is beautiful. You basically use optical tweezers, which are lasers, to trap individual atoms. So you can just, you have a vacuum chamber, and then you just, using n lasers, you capture n, I would say n beams, maybe single laser that is split in n beams. You can capture n atoms, move them individually, and make them interact. And the way they interact is that when 2 atoms that are excited in a Rydberg state come close, their energy changes, right? So neutral atoms were in the ground state, their interaction is very weak, but when they're excited, the dipole, there is more susceptibility. I mean, you have a larger interaction between the atoms. So what you do, you basically excite the atoms and then bring them together, and this creates some interactions between the atoms. So the native gates are shuffling. Shuffling means you can just move, and this is really important because you can get to arbitrary geometry, right? You can just move your atoms whatever you want. If you have a picture in mind, there is this beautiful movie of the Super Mario.
I think it's shuttling, the term.
Shuttling, sorry, thanks. Yes, thanks a lot. Well, you also shuffle them, but yes, shuttling is a much better word, thanks. So the idea is that you can move them in space, and then you can create any arbitrary geometry. Okay, this is just a picture of an optical table to say that this is, okay, that's how it could look like. And then, of course, there is a vacuum chamber, and you need to combine everything. So what were the key ingredients of this first experiment? I mean, first in this series of 3, of course. So they realized a very important model of condensed matter, which is called the Kitaev Hamiltonian, on a honeycomb lattice. So a honeycomb lattice is a lattice that is drawn here, is done with hexagons, and the Hamiltonian that is realized is a very strange Hamiltonian. Of course, it's strange for a normal person, but very natural for Kitaev. So Kitaev said, well, if I look at a single atom, I see that the single atom has free connection, 3 edges. And so then I say, well, each of these 3 edges, on one edge, they will apply an XX coupling, on another edge, YY coupling, and on the other edge, ZZ coupling. So that was the idea of the Kitaev model. So you have an Hamiltonian on a honeycomb lattice, and the interaction itself depends on the bonds. So some bonds are X, some bonds are Y, some bonds are Z. Now, of course, although there are materials that have honeycomb geometry, to have that particular interaction is really tough. So that's why simulating it on a quantum computer was was very interesting. And of course, you need to be able to prepare a honeycomb lattice. So that's why they use neutral atoms in which they could move the atoms in any geometry and build, let's say, a honeycomb lattice. And then what they did, essentially, the way to do it, so you take these two atoms, and then you make them, you move them closer so that they have an interaction between on the red bond. Then you move them closer and they interact on the orange, and then you move them closer and you interact on the blue. And yeah, that's it. Yeah, this model is very interesting because it can map to free fermions model, to Majorana fermions model that live in a gauge field. I'm not an expert, and we also definitely don't have time to explore the model itself. But there was a reason why this model was considered, and I would like to focus on the tricks that are more relevant to the implementation. So let's say you have the Hamiltonian. Okay, I want to realize this in a quantum computer. What are the challenges? Challenge number one: when you talk to a condensed matter physicist, for him or for her, if you give an Hamiltonian, the first thing they'll do in their mind is find the ground state. Okay, that's how condensed matter physics brain works. They get an Hamiltonian inside and they think about the ground state. So the beautiful properties of this Kitaev model and the phase transitions that they involve with is related to the ground state. So you need to be able to prepare a particular the ground state of this Hamiltonian. And this is really challenging because the ground state, it comes out, it has a huge amount of entanglement. It has what is known as long-range entanglement. So preparing that, it's not, usually in a quantum computer, you start with 0, 0, 0. That's the initial state of any quantum state with 0, 0, 0. But here you want to start in the ground state. And starting in the ground state is complicated. So they used a very nice trick that, as I mentioned, the ground state has a lot of entanglement. So in order to create it, you would need to apply a lot of gates. And they sort of solve this problem by using ancillas. So they use some extra qubits that allow them to prepare the ground state more easy. So sometimes this is something you need to keep in mind, that how do I prepare a ground state? And sometimes there are techniques that allow you to add more qubits to get a shorter circuit. And that's very important. So using this, they were able, so this is a phase diagram. So the phase that you see, there are three parameters, Jx, Jy, Jz, and this is the phase diagram in these free coordinates. And what they prepared here was the ground state of this particular Hamiltonian. So this is also a trick which is very common, which is in preparing the ground state of a complicated Hamiltonian is very, usually it's very hard because you don't know what the ground state is. So in many models, there is a specific point. Let's say in this case, it's the Jz is equals to 1 point. So this is a specific point in the phase diagram for which the ground state is easy to prepare. So the preparation using ancillas doesn't allow you to prepare any given ground state. It allows you to prepare a ground state in this particular point of the phase diagram. Okay, good. Then what they did, they said, we want to probe a phase transition. So you see this phase diagram has 4 phases, which are topological, etc. So they wanted to probe the phase transition. So they wanted basically to move from the blue point, which is a state they know how to prepare, to either this black, dark blue or gray point. So they wanted to take this Hamiltonian and bring it either here or there. And the way they did it, so how do you prepare? There are different ways to prepare a state, and one way is to prepare the ground state of this Hamiltonian, and then slowly change the Hamiltonian so that using the adiabatic theorem, if you were initially in the ground state, you will end up in the ground state. So that's what they did here. They started in the ground state of this Hamiltonian at a particular point, and then slowly changed the Hamiltonian until they got to the final state. Now, how slowly? Of course, would you like to be really, really slow? In practice, they did 6 steps. Okay, so there were 6 layers of adiabatic. An adiabatic protocol is a protocol that takes an infinite number of layers. This infinite was 6. It was very small. This is related to the fact that the model itself was small, so there is a gap and it protects, etc. But in addition to that, what they did, they also optimized these steps. So instead of doing the steps, basically tells you start from this ground state, you want to end up in this ground state. So you can do it like 1, 2, 3, 4, 5, 6. I mean, you can use these steps in a linear way, or you can optimize it better. So that's what they did. I'll mention the relation to flow K in a moment. Okay, so this is the experiment. You start in the ground state, you prepare the ground state, you need to check that you've prepared it, and then you want to either go to the dark blue or to the gray point. And this was one of the main results. For each of these examples, I have 3 papers. I will highlight one key result, just because so you have a feeling. And what you see here, this is the churn number. So the churn number is a property of the fermionic model, not of the, which you can compute in using spins, but it's a property of the fermions. And as you can see, the churn number is always an integer number. And as you can see, in the initial point, the churn number was 0. In the dark blue point, the churn number was still 0. And in the gray point, the churn number was 1. So the fact that churn number changed from 0 to 1, it means that there is a phase transition. Okay, so the idea is everywhere in the light blue area, the churn number would be 0, and everywhere in the light gray area, it would be 1. Of course, they checked only 2 points, but fine. Okay, the result is beautiful, but how they did that? So question number 1, how did they measure the churn number? Because as I mentioned, the churn number is the properties of the fermionic state. And in the map, there is a mapping between spins and fermions, but measuring the churn number using spins is a very non-local object. It's something that requires you to compute the correlations between essentially all the spins in your system. It's very complicated, very, very complicated. You cannot. So this is not the direct measurement of the churn number. The churn number is a topological number, so it's not a local number that you can make. It's not a local observable. So what they really did. What they did, they actually measured spin correlations, a certain number of spin correlations between neighboring spins, and then they used, they evaluated the churn number using the learned parent Hamiltonians assuming free fermions. See appendix for details. So this is the idea. So you assume that this is a system free fermions. Then you ask yourself, if this is system free fermions, what would be the best fit of the churn number? Now, for free fermions, the churn number is always an integer. So essentially, what they are doing here, they're not measuring the churn number. What they are doing is, what would be the best fit? What would be the best fit for the churn number? And then, of course, you get a real number because the churn number is always an integer. So you either get 0 or 1. Well, okay, it's nice because you get 0 on this point and 1 on the other point, so it sort of works. But considering they have only 3 points, there is at least a 25% probability that they got it by chance. So again, you can look at this in 2 ways. Either say, well, they're cheating. They're not measuring anything. This is just not interesting. Or you can say, well, they were really smart. They could not measure the churn number. They could measure these correlations. You see, they measure XX, YY, ZZ, ZYY. These are all correlations, spin correlations. So you measure all sorts of small spin correlations, and then you ask theoretically what would be the best fit for such a model. So I think this is beautiful. It's a very nice idea of how to extract from some noisy measurement a topological number. You don't necessarily want to measure the number itself, as long as you have an indication that what you are doing is correct. Okay. So in particular for this model, we know this model can be exactly solved. So we know what the churn number is. There is no meaning. The beauty is to realize it in an experiment. That's the beauty. What is the value of the churn number was already known. Okay, good. Example number 2. Example number 2. This was done using actually a quantum computer by IBM. As I mentioned, epsilon is 0.2%. They use 40 qubits out of the entire system. And what I like about this work is that there is no researcher from IBM who was involved. Almost no research. It was really done as a quantum computing on the cloud. People access those quantum computers, did the experiment, and then what was beautiful is that they compared the result from the quantum computer to a real material. Okay, so that was the idea. The idea was to compare the result of a simulation with a real experiment on a real material. So I think this is, I really like this experiment. Okay, again, it was done on IBM quantum computer, but not by IBM itself. It was done by users. People use it. These are experimentalists. They have materials. In particular, they have a material that behaves as a one-dimensional antiferromagnet. So this is the model itself. And what they did, they wanted to compare the Green's function. So the Green's function is the correlation function between 2 points. In a moment, I'll explain you. And the way they did it, they basically, okay, you see, there is ground state preparation. Okay, question number 1, how do you prepare the ground state? And the way to prepare the ground state was using the same trick I mentioned before. So they basically started with an initial state which is easy to prepare, and then they adiabatically moved they adiabatically changed the Hamiltonian so that you will end up in an interesting non-trivial Hamiltonian for which you have an approximate ground state. Then they applied the local perturbation. The local perturbation is like the starting of the dynamics. They did the dynamics and then measured. Okay, so the local perturbation in the middle is to compute the Green's function. As you know, the Green's function is just the correlation function of the spin at point I and time 0, and the spin at point j time t. This is G1 ij t. So you want to compute the correlation between a spin at initial position and the final position at a later time. And this is done here. So you prepare the ground state, you apply a perturbation. This is at point I, or well, okay, j, whatever. And then you measure it at point I. So you have the correlation between point I and point j, and the time is controlled here, right? So by changing how long we evolve the time, you have the time evolution. So okay, this is how it looks like in real space, okay? So in real space, what you see, on the x-axis you have the number of qubits, on the y-axis you have time, and you see that and you have a comparison between the quantum computer on the upper side and on a numerical simulation on the lower side. This is a numerical simulation done using matrix product states, which is a powerful numerical technique, which is excellent for 1D systems like this one. And you see there is a beautiful equivalence, at least for short times, right? For short times, there is these equivalence work very well. If you go to longer times or larger number of qubits, you see that the signal here is a little bit lost. We expect what you would expect for the quantum system from the numerics. If you can think of each of these squares, essentially it's like a 2-qubit gate, right? Because you are applying you are applying a 2-qubit gate for it. So you can think of a square, right? And you see this. The size that works is basically something like a 10 by 10 square. So it's something like 100 2-qubit gates, which is in comparison with what I said before. You can go on further, but then the signal is very weak. So if you want to have a good, working method, you will need to focus on this square here, which is a small system for a relatively short time. And what was beautiful is, again, they were able to compare it with real experiments. In the experiments, you don't do it in real time and real space. You do it in momentum space. So the way you take your material. This is this material here, potassium KCuF3. This is the material, and what you do, you basically come with incoming light that is given momentum, and you observe the absorption. You measure the absorption as a function of momentum and energy. Okay, that's the idea. And you see that this is the experiment on the lower plot, and the upper plot is basically the Fourier transform of this figure. Okay, the absorption spectrum in momentum and frequency is essentially the Fourier transform of these computations. So they computed in real time and real space on the quantum computer. Then they just do a Fourier transform and they compare it with the result on the quantum computer. On the real experiment, and I think it's nice. I mean, you can really recognize these spin-ons branches very, very, very nicely. So, okay, it's a non-trivial result. I mean, it's already doing something, computing a property of a real material. So I think this is this is really nice. Questions until now? Okay, then if not, let's move to the third and last examples I want to make bring today. This is actually an example from the third from the third system we mentioned. So I meant the first example was from neutral atoms. We had superconducting circuits. This is about trapped ions. This is the quantum computer by Quantinuum. It's like very nice. It looks nice. But also the epsilon is really small. So remember that I gave you the number of 0.2% for superconducting circuits. Here in Quantinuum, the 2-qubit gate error is 0.06%. It's 5 times lower, which means that the number of 2-qubit gates that you can implement is 5 times 100, 5 times larger. So you can already implement a circuit with 1,000 2-qubit gates. The downside of this is that the quantum computer by Quantinuum is really expensive. And the reason it's expensive is because it's very slow. So applying the 2-qubit gate, the time that it requires to apply a single 2-qubit gate is about 1,000 times longer than the times it takes to apply 2-qubit gate on a superquantum circuits. It's a difference between, say, microseconds and milliseconds. So it's really a huge difference. And so, every experiment you do, just need more time. So they will be able to run less experiments, and so they need to charge more money. That's the way it goes. There are other trapped ion quantum computers which don't have such an amazing small 2-qubit fidelity, and they are cheaper. So, okay. What are the key ingredients of this experiment? So this was about the two-dimensional transverse field Ising model. So the two-dimensional transverse field Ising model, it has a ZZ component, that's the Ising model, plus a transverse magnetic field. And here I want to mention this digitalized Floquet. So when you try to simulate the dynamics of a quantum system, for instance, I think this scheme is nice to understand. So the x-axis is time. Let's say I focus on this qubit. So this qubit interacts with 4 different qubits, right? With the qubit up, left, right, and down. But I cannot apply the 2-qubit gates, all the 2 qubits at the same time. So this qubit here, I can make it interact with the upper qubit. I cannot make it interact with all the 4 qubits at the same time. So what you do it discretely. So you first make it interact with the upper qubit, then make it interactive with the lower qubit, then with the qubit on the left, and then the qubit of the right. So you need to do it in a discretized way, and then you apply the transverse field. Okay, so this is called digitalized dynamics. You need to take the Hamiltonian. In principle, what you would like to have is to have all those 4 terms together. I mean, up, down, left, right, and the transverse magnetic field in the same time. This is what is written here. This is the Hamiltonian. But in practice, on a quantum computer, you split those times, and that has some influence. I mean, this is also an interesting research question. What is the difference between the dynamics of the original Hamiltonian and the dynamics of the Floquet, or digitalized? It's called Floquet because it's Floquet means periodic. So it's a periodic Hamiltonian. Instead of having just this Hamiltonian, you have transverse field, Z, 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 Z. Transverse field, Z, 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 and so on and so forth. Okay. As I mentioned, this is a quantum computer which has, amazing low error. So they were able to simulate a lattice of 7 times 8, so 56 qubits, for 20 time steps. So that means that you have approximately 4,000 gates. And actually, this 4,000 is even larger. It's 4 times larger than the number I gave you before, right? If you remember, according to the thumb rule, you should be limited to 1,000 2-qubit gates. They were able to implement 4,000 gates. And how they did that? Well, to do that, they used a method called error mitigation. And I think that Eli will tell us about error mitigation. We'll learn about error mitigation in 2 weeks from now, how you do it in practice. But let me just give you the idea. So what is the idea? So the idea is you would like to mitigate the error. You would like to have less error. But you cannot because you have a finite amount of error. So what you do something which I have to admit, the first time I heard about it, I thought it was like junk. I mean, but it works. So what is the idea? Instead of subtracting the noise, you add more noise. But what you do, you add more noise of the type that already exists. So you take your quantum computer, you calibrate, you measure the amount of error that you have in each gate very well. So you know exactly which error you have. And then you run your quantum circuit. Okay, you get results. This would be artificial noise rescale. So this would be artificial noise rescale 1. You don't rescale the noise. Then you say, okay, nice. Now I want to, let's say, double the noise. How do I double the noise? I add by hand the gates that correspond to the noise. So I run another quantum circuit that includes the original quantum circuit plus the noise. And then you do it 3, 4, or 5 times, etc. And what you see is that you get this curve. So the continuous curve, it is the one you get from the experiments. In the experiments, you get the one without noise. This is artificial noise rescale 1. And then you have many, many more points with more noise. And what you do, what you really are interested in is without noise. So you extrapolate back, right? So you fit it to an exponent or some other function, whatever, and then you fit it back to what would be the result. So and then you get, as you see, you get a result which is much closer to the original result. So if the original result was 1, okay, it's normalized. So if the original result was 1, you see that you get and the noisy experiment would give you 90. By doing this zero noise extrapolation, you can get much closer to the original result. It's called error mitigation. And as I mentioned before, this error mitigation really requires you to run more circuits. So you just run, first of all, you need to calibrate very well the noise. So you need to know exactly which type of noise you have on each t-qubit gate, because if you just add some noise that is not the one you have in the experiment, it's not worth. So you need to first calibrate the system, then run your quantum circuit, then repeat to the quantum system with more noise, and many, many, many times, for different values of noise. And well, how do you add noise? Just run circuits with additional noise. And you need to average over those noise realizations. So it really requires you to increase the number you need to increase the number of circuits that you run. So it's really much more expensive. I mean, this was a collaboration with Quantinum. I'm sure that they didn't pay for running on the quantum computer. But the cost of running this experiment is, if someone were to pay, it would be really, terrible. Really, really significant. Because the Quantinum is expensive, it's slow, and you need to repeat it many times. But the results are significant. Why? Because they compare it with state-of-the-art numerics. So some of the authors are, some of the best, of the experts in these matrix product states, and they really ran the Hamiltonian using the best available matrix product state. So this is one result, as you see. So on the x-axis you have time, or the number of steps. In the y-axis you have some observable. Okay, so this would be the whatever. This is the total magnetization square. It doesn't really matter the observable itself. And we see several things. So you see the continuous line of numerics, and this chi is the size of the matrix for the state. So this is like poor numerics. This is the numerics I would do. This is better numerics, even better, and so on. This is already, very heavy numerics, 4,000 heavy numerics, and then you extrapolate. Also here, you say the chi is the approximation level, so is the size of the matrices that you're using for your approximation. So the larger it is, the best you can. If chi was infinity, it would be the exact numerics. But of course, then you wouldn't be able to run it. So you have different values of this parameter, and you try to extrapolate it, and you get a curve. This is the continuous purple curve. In the experiment, what you do, you run the experiment without noise. This is the blue. Okay, the blue is the one you run and you see it's very far away. Then what you do, you do the NA. NA means noise amplification. So the green curve is also an experiment with more noise. Okay, so blue is the best experiment you can perform, and the green is an experiment which you added noise. And then you do the zero noise extrapolation. So using the value without noise and with a lot of noise, you try to extrapolate what would be the value without noise. That's zero noise extrapolation here. So you see there is zero truncation extrapolation. This is the numerical extrapolation, and this is the experimental extrapolation. And they sort of match, right? It's beautiful. The theory and the experiment match. The second curve is a curve which is done is a different regime. Doesn't really matter. It's a different initial state. And what you see here is that when you try to extrapolate the numerics, you get some physics. You see that when you improve the numerics, it doesn't converge. So it means that essentially you don't know where it's going. So while here it's converging, so here for small times, fine, it's very easy to compute. For larger times, you see that the numerics is going, I mean, just, you don't know. I mean, you don't know how to extrapolate. While in the quantum computer, you seem to have a result. So the idea here is to say that the quantum computer is now competing with the best available numerics. I mean, this is a very serious, I think this is probably, as far as I know, this is the first evidence for quantum simulations, so not the quantum supremacy, for quantum simulations of this type. This is the first evidence of a quantum computer that is already competing with the best available numerics. There were previous attempts, but then the numerics was able to sort of mimic this result. Here, for the moment, this was not possible. So yes, I think this is a very significant result. Okay, great. So I think we are about to conclude. Of course, as I mentioned, I brought only 3 examples, and there are many more. There is a 2021 time crystal experiment. I mean, Google, they have a beautiful machine, and they are also very good in public relations, so everyone got excited about a new phase of matter, which is a time crystal. By the way, the time crystal is a phase of periodically driven system. So the fact that the system is periodically driven, this Floquet idea, may be important. One can say it's a bug, but you can also think it's a feature. So the fact that you need to discretize this time evolution can be considered as a feature for the time crystals. Then they did an experiment. There is a lot of discussion. Maybe this experiment was not even correct, but anyway, they did simulation of something related to quantum wormhole, and then the public got crazy because the wormhole is related to the black hole, and the black hole will erase our entire world. But don't worry, this is not a real black hole. It's not a real wormhole. It's just a simulation of a model that has something to do with wormhole. So no danger. There is an experiment here also by Tum. Realizing a Floquet topological phase. So this was already a periodical driven state. This is a periodical driven state that also has topology in it, so even more interesting. And this very recent paper, 2601, about quantum chaos. And in fact, I'm mentioning this because Michael Fegelman, who is one of the authors, is going to give a presentation of this work next week. So I really encourage, if you find this interesting, this line of thought of work, I really encourage you, and you can find on the kernel website the link to the Zoom to attend this event. It's going to be an in-person event here at Bar-Ilan, but you can also connect using Zoom. So I mean, I think it's exciting to have the people who really did the work who can present it. I tried to avoid it, but I could not do it. To present, one slide about our own group. So we've done several quantum simulations with small systems. I see some of my co-authors here. So it's you can read about them. And also we realized them on the quantum computer, and we measured how close it was to the theory or not. These were maybe a little bit older machines and smaller number of qubits. Let me conclude. So I think the main message I want to convey is that quantum simulations with today's computer are possible, and I really invite you, especially the kernel members. I would even say, I even request you, I really encourage you to think about which quantum simulation can I perform. And we've seen that there are different platforms, that they have different connectivities, different performances, different 2-qubit gates, fidelities. The number of gates that you can get to, depending on the platform, goes between 100 and 1,000, I would say easily. And if you're really serious about it and you use noise mitigation, again, it means that you have more budget and you work harder, you can get to maybe a factor of 10, maybe. So I think reasonably one can get to 1,000 gates. If you want to go beyond that, you will need to work hard. If you want to get beyond 10,000, forget about it, at least for now. The key ingredients you will need to think about is which state do I prepare? What is the initial state? You can prepare it variationally using ancillas, maybe using a specific integrable Hamiltonian. And you need to think about what is the Hamiltonian you need to realize, how you translate the Hamiltonian to gates, what is the connectivity. And don't forget that you will often, if you are thinking about the simulation, you will always need to do it in a digitalized way. So instead of having continuous time, you will need it discretely, which is related to these periodically driven Hamiltonians. And the main message is unity makes strength. So as you've seen, many of these works were written by many authors, and I really encourage you to maybe work together. And this is also why we're having an in-person meeting, because I think doing learning one from another is important. Very last two slides. First of all, how much does it cost? Okay, there is a C missing here. And actually, the huge news, the amazing news from IBM is that they are now offering a significant amount of free credits for academics, which you don't even need to write a proposal. You just log in, and you have several, up to 2 hours per year. There is a pattern. You can learn about it, but I think this is something that allows you to do already enough, sufficient. Of course, you need to prepare yourself, right? You need to first run it on the simulator, see that it sort of makes sense before you run it on the quantum computer. But this offering, I think it's now very significant. And at Kernel, we also have dedicated funds for that. So if you are a Kernel member and you have run out of your IBM quantum credits, please come to us. We can offer more. We have more resources. And also the same goes if you want to use another platform where you don't have free credits. So please talk to us. The main message is we can do it. The center can support you and can support also the budget for running on the quantum computer. So that's not going to be the main obstacle. For next time, we'll have actually a hands-on tutorial on how to use Qiskit to run a quantum simulation or in general quantum circuit. In order to get ready for that, you need to do two things. First of all, you need to install Qiskit. It's basically a Python pip install. It's a Python extension. You need to register on IBM Cloud. In order to do that, you need a credit card, but there is a way to make sure that the credit card is not used. So don't worry, the credit card is used only for identification purposes. It will not be charged. There is a way to sort of protect the credit card so that you cannot.
Emanuele, is this the quantum cloud or IBM cloud?
It's the same. You need to register on the IBM cloud, which also include the IBM quantum cloud. But you need to have an account, a verified account with the IBM cloud. Then you go, once you have registered, you go in and you define something called an instance. The instance is essentially the budget. So it's telling you, for instance, there is a free instance. So if you create a free instance, it will use only free times. It will never use your credit cards. Or if you have credits, you can use the credits. So you define something called an instance. It's very easy to find. You go on Google Quantum Cloud, and there is a button with instance. If you have problems, ask me, but it's really simple. But this is a step you need to do. Once you have defined an instance, you also generate an API code. There is also a button, generate an API code, so you get a password. And then once you have done these two steps, you go and you install the Qiskit IBM runtime. The Qiskit IBM runtime takes as input two things: the name of the API code, which is basically your account, the account name. It's a code to create an account name, and the name of the instance, which you have created. So it's actually very simple. I have to say, before I tested it, it actually works very smoothly. I already had the account, so it was easier. I already had the instance. But once I had these two ingredients, in 5 minutes, I was able to run it. And as you can see, I used already 2 seconds out of my credits. And so now instead of having an hour, I have 59 minutes and 58 seconds. And I was able to run a circuit with 1,000. It's a very simple circuit. It doesn't matter. It was just creating the free qubit. You will see, you have all the codes here. You just need to copy paste the code and your IBM Cloud instance. So I really, these are, I would say, mandatory steps in order to join our next. I would say, okay, these are mandatory steps if you want to get the best out of the next tutorials. If not, you can just connect, but that's not. This is going to be partially useful. If you want to enjoy the tutorials fully, I really encourage you to do these steps. And if you get stuck, please address me, please address Eli, Arbel. I just want to say that if you already had a IBM Cloud account and you did not verify it using a credit card, you may run into problems. So you may need to open a new account. The accounts that are not verified by credit cards, after a few months, they expire, and it's not very clear at the moment how to put them back. So if you cannot pass the credit card verification, probably it's not a problem with the credit card, it's a problem with the account being an old account that has not been verified for long times. So my workaround, and I've been talking with IBM for a long time, my workaround was to just create a new account. That's the way I suggest. But then it's smooth. I mean, actually, I was surprised. I mean, I remember some time ago, on the runtime, it was very complicated. But here, I think it's now I think it's very easy. Yeah. Okay. So,
Emanuele.
Yes.
Hi. Can I comment?
Yes. Sure. Please do so.
Yeah. Sure. First of all, thanks for this talk and in general this series of presentation. Really happy for the opportunity and taking part in this, and looking forward for our next meetings. So just about the next session, which Gadi from our team is going to deliver. I highly encourage everyone to go through the steps that you described, Emanuele, and kind of log into the IBM Quantum platform through IBM Cloud. And just like, again, small comment to Ram, everything now is IBM Cloud based. The old, quote unquote, old Quantum platform, everything was migrated to IBM Cloud. So everything is now through the IBM Cloud platform. So a minor comment regarding the next session, Gadi is not going to use actual quantum hardware during his hands-on class and demonstrations. We are going to use a simulator which can be run locally. Actually, the simulator, which is a kind of a built-in component of the Qiskit SDK itself. So besides the Qiskit repo installation, nothing else is required. In this session after that by Safrir about the Qiskit runtime, error mitigation method, etc. Access to the IBM Cloud Quantum platform would be more needed, I would say. But still, for the sake of education, next week, please try to log into the IBM Cloud. But if you encounter problems and it takes more time, that's fine. For next week, we use local simulator. Yeah, that's it. Small comment.
Okay. Well, thanks, Eli. So I'm actually proud of myself. We are like in perfect timing for 2020. It's the first time I delivered these presentations. I didn't know exactly. I'm glad I planned it at least correctly in time. If there are, just more remarks or questions, if not, we'll rejoin next week. Okay, so thanks everyone. We'll send out the recording and the slides to everyone who registered, and see you next week.
Thank you, Emanuele.
Thank you. Bye-bye.
Thank you, Emanuele.